Hey Cal 2 students, welcome to lecture number 4 in Cal 2. We're going to start off with derivatives of the exponential function. We already know that the derivative of e to the x is e to the x. E to the x is the function that is its own derivative. What we're going to do now is extend this result a little bit further and look at e to the x, or the exponential function, where the chain rule comes into play. If we have e raised to the power of a function, this is a composite function. This is the function e evaluated at a function g of x. G of x is the inner function, and the outer function is this, e evaluated at something. This is the outer function. The inner function is g of x, the exponent. So when we compute the derivative of e raised to the power of a function, we have to use the chain rule because we're computing the derivative of a composite function. To set the stage for using the chain rule, let's make this observation. Our outer function is e evaluated at something. Now we know that the derivative of e evaluated at x is e evaluated at x. So the derivative of e evaluated at something is e evaluated at something. This is what the derivative of the outer function looks like. And I guess that makes sense. E to the x is the function that is its own derivative. So e raised to the power of something should be its own derivative. Let's do the chain rule. We're computing the derivative of e raised to the power of g of x e raised to the something is the outer. G of x is the inner. Now let's remember what the chain rule tells us. When we compute the derivative of a composite function, we get the derivative of the outer evaluated at the inner times the derivative of the inner. I'm going to write that down. We get the derivative of the outer evaluated at the inner times the derivative of the inner. The outer function is e evaluated at something. Here's the outer function. The derivative of the outer function is e evaluated at something. There's the derivative of the outer function. And what do we do with it? The chain rule says that we evaluate this at the inner function. We plug the inner function in here. And then to finish it off, we multiply by the derivative of the inner. Now, let me just repeat that result. The derivative of e raised to the power of g of x is e evaluated at g of x times g prime of x. So in general, the derivative of e to the power of anything is that same thing, e to the power of anything, times the derivative of the exponent. Sometimes we'll see this written in a book this way. U will be some function of x. U will be our g evaluated at x. And the derivative will be e evaluated at u times the derivative of the exponent. Sometimes we'll see the formula written this way. The bottom line is this. If we have the derivative of e raised to the power of some function, e to the power of some function, we get that same thing, e to the power of that function, times the derivative of the exponent. E to the power of a ham sandwich is e to the power of a ham sandwich times the derivative of that ham sandwich. Let's do some exercises. We're computing the derivative of e to the power of sine of x, and we get e to the power of sine of x times the derivative of the exponent. We're computing the derivative of e to the power of x squared plus 2x. We get e to the power of x squared plus 2x times the derivative of the exponent. Yeah, let's try a somewhat pathological exercise. Just to make sure that all the rules that we're learning about logarithms and exponentials are consistent. Derivative of e raised to the power of natural log of x is e raised to the power of natural log of x times the derivative of the exponent. Derivative of natural log of x is 1 over x, right? What is e raised to the power of natural log of x? Isn't that just x? So we have x times 1 over x, and that's 1. The derivative of e raised to the power of natural log of x is 1. Really? Well, let's do this a different way. I get to use my colored markers here. I love that. e to the natural log of x is just x, right? So we're computing the derivative of x, and that's just 1. Okay. We did this 2 different ways. We got the same result each time. Bravo. Bravo. Let's do some more of these. Wait a minute, wait a minute, wait a minute. This is a derivative. Oh, well, we'll do a derivative. We have the natural log of something. Natural log of g of x. We compute the derivative, so we should get 1 over that function times the derivative of that function. 1 over this piece of junk. Times the derivative of this piece of junk. Well, the derivative of e to the x is just e to the x. The derivative of e to the negative x is e to the negative x times the derivative of the exponent, which is -1. Remember this example. We're going to have an exercise in our homework where we have to compute the integral of this thing. This exercise may give us some insight as to how to approach that. We have e to the power of tangent x. If we compute this derivative, we're going to get e to the power of tangent x times the derivative of the exponent, which is secant squared x. This is pretty easy, isn't it? Okay, computing derivatives of e to the power of a function. Not much of a problem. Let's go to antiderivatives involving exponential functions. We'll do the simple stuff first. Remember, e to the x is its own derivative. In other words, e to the x is the function that we compute the derivative of to get e to the x. So the antiderivative of e to the x is going to be e to the x plus some constant. Let's look at some simple examples first that don't require the chain rule. Here we're integrating a constant times a function. And the way we do this, the way we integrate a constant times any function, we write down the constant, and then we ignore the constant and compute the antiderivative of the function. And then we multiply them together. What could be easier? Now, I'm going to have to make this a little bit harder. Not much, but a little bit. In the most general sense, we're computing the antiderivative of the sum of two functions. So we compute the antiderivative term by term, one term at a time. We'll do this term first. And this term is a constant times a function. We know how to do that. The way that we compute the antiderivative of a constant times a function, we write down the constant, and then we look at the function and compute its antiderivative. And then we move on. We do the antiderivative of the next term. It's a constant times a function also. So we write down the constant, and then we ignore the constant and compute the antiderivative of the function. The antiderivative of sine of x, what is it? Negative cosine of x, right? Negative cosine of x. And then we add the plus c. And that gives us 1/2 e to the x minus 3 cosine of x plus c. Now let's take into consideration the chain rule and U-substitution and what we have to do when we have the integral involving not just e to the x, but e to the power of some function. Remember, the derivative of e to the power of g of x is e to the power of g of x times the derivative of the exponent g of x. So if we integrate e to the power of g of x, we're going to want to have the derivative in the same expression. This is a composite function. So we say, do we have a composite function? The answer is yes. E to the power of g of x, where g of x is the inner function, and our rule of thumb, we let u equal the inner function. The other criterion that we look at, do we have an approximate function derivative pair? So do we have a function and its derivative or a constant multiple of the derivative somewhere else? And we do. We have g of x and g prime of x. So here's the function of the function derivative pair, and here's the derivative. Our rule of thumb, we let u equal the function of the function derivative pair. So u is equal to g of x. Beautiful, beautiful, beautiful. The next step in the process is to compute du. U equals g of x. Du dx is g prime of x. And that means du is g prime of x dx. So here's what our integral looks like. E to the power of g of x times g prime of x dx in terms of u, this is e to the u. In terms of du, this is du. In terms of u, we just have e to the u du. Well, isn't that exactly the same as e to the x dx? The only difference between this and this is the name of the variable. So whatever this does to x, this is going to do the same thing to u. And now that we've rewritten it in terms of u, let's go back to our original expression. U and g of x are the same. In terms of u, this is our answer. In terms of g of x, this is our answer. Now, we're not really going to analyze it this way when we do it, but we want to go through the mechanics of it so that we can take away some important points. Important observations. When we're computing an integral containing e to the power of a function g of x, we're going to need a factor of g prime of x somewhere in the integrand to serve as part of our du. So in other words, if we have e to the power of g of x, almost certainly u is going to be g of x, and du is going to be g prime of x, g prime of x dx, or possibly g prime of x dx with some sort of constant here. Du is either going to be g prime of x dx, or du is going to be some constant times g prime of x dx. So if we see e to the power of g of x in the integral, look for g prime of x in the integral too. G prime of x, or a constant multiple of g prime of x. That's the key. Anytime we see e to the power of a function in an integral, look for the derivative of this exponent somewhere else in the integral. Almost always, u is going to be the exponent g of x, and du is going to be g prime of x dx with perhaps or a constant multiple of that. Anytime we see e to the power of a function in the integral, look for the derivative of that exponent somewhere in the integral. Almost always, u is going to be the exponent of e, and du is going to involve the derivative of that exponent. So we need to find the derivative of that exponent in the integral somewhere. Let's do a couple or 2 or 3 or 10 or 15 examples, okay? Here's a good one to start off with. E to the power of x squared plus 2x times x plus 1 dx. Do we have a composite function? We sure do. And maybe I should actually write down what that composite function is. E to the x squared plus 2x This is the inner function. And our rule of thumb is to let u be the inner function. Do we have an approximate function derivative pair? Do we? X squared plus 2x, what's the derivative of this? The derivative of the exponent is 2x plus 2. We have x plus 1. X plus 1 is a constant multiple of the derivative of the exponent. So yes, we do have that approximate function derivative pair. This also goes well with the point that we just established. If we see e raised to the power of a function in an integral, look for the derivative of the exponent somewhere. And we have it right here. This is 1/2 the derivative of the exponent. So we are looking really good. Our rule of thumb here, we let u equal the function of the function derivative pair. So u is going to equal x squared plus 2x. And both criterion A and criterion B suggest the same choice of u. So almost surely this is going to work through U-Substitution. Next, we're going to compute du. U equals x squared plus 2x. Du dx is 2x plus 2. du is 2x plus 2 dx. And I'm going to leave about one line blank here. Now I'm going to analyze my integral in terms of u and du. In terms of u, what is that much? This is e to the u, right? Now, what about this? I don't see exactly this up here, but I think I can turn the right side of this equation into x plus 1 dx if I multiply both sides by the right constant. Excuse me. What constant would I have to multiply both sides by here to make the right-hand side look like this? 1/2? Let's do it. 1/2 du is x plus 1 dx. So what is x plus 1 dx? It's 1/2 du. We rewrite the integral in terms of u and du, and we have a constant factor here in our integrand. We can just take that and move it out front. And this is exactly why we don't have to have an exact function derivative pair. If we just have an approximate function derivative pair where we're only off by a constant multiple, as long as this is a constant multiple of the derivative of that function, we're okay. Because we can always take that constant that we're off by later on and move it out in front of the integral sign. Now step 4. Integrate. The antiderivative of e to the u du is just e to the u plus c. Now we know what the answer is in terms of u. It's 1/2 e to the u plus c. We want our answer in terms of x. And back in step 2, we have the rate of exchange between x and u. 1u is equal to x squared plus 2x. So 1/2 e to the u is 1/2 e to the x squared plus 2x plus c. Well, that was pretty good. Let's do a couple more. This one's a nice one. We have a composite function, e raised to the power of tangent x. And whenever we see e raised to the power of a function in an integral, we look for the derivative of the exponent somewhere in the integral. The derivative of tangent x is what? Secant squared, right? And here's what I think. I think that unless we can find a secant squared somewhere in this integral, we are not going to be successful. So let's see what we can do. Is this our secant squared? Let's see. There is a relationship between cosine and secant, isn't there? Secant is 1 over cosine of x, or vice versa. Cosine of x is 1 over secant. So maybe I want to rewrite it like this. And maybe I want to rewrite it again. Now this is looking like something. This is secant of x squared which is the same as secant squared x. The only difference is the style of notation. So all of a sudden, this doesn't seem all that formidable. Let me rewrite the original expression. This doesn't look daunting at all now. It's amazing how helpful it can be to rewrite an expression once or twice or even 3 times like we did over here. So let's see, 1a, composite function. Yes. E to the power of tangent x, and tangent x is the inner function. Our rule of thumb is to let u equal the inner. So it looks like u is going to be tangent x. Let's look at our second criterion. Do we have an approximate function derivative pair? We sure do. As a matter of fact, we went to great lengths to rewrite this expression so that the derivative of the exponent would jump out at us. So yes, we do. We do have an approximate function derivative pair. In fact, it's exact. Secant squared x is exactly the derivative of tangent x. And our rule of thumb is to let u be the function of the function derivative pair. So u is tangent x. Criterion A and criterion B both tell us to let u equal tangent x. So let's compute du. Derivative is secant squared x. Now I'm going to analyze my integral in terms of u and du. In terms of u and du, what is this much? Isn't that e to the u? And in terms of u and or du, what is this? It's du, isn't it? So this one is going to work out nicely. And now we integrate. And just as a side observation, we went to a great deal of trouble to rewrite everything in terms of u. We're not going to integrate it in terms of x. We analyzed everything in terms of u. We rewrote the integral in terms of u. We're going to perform the integration in terms of u too. So don't get here and then go back and try to integrate this. We've gone to great pains to write everything in terms of u. We're going to perform the integration in terms of u. And this is a well-known form. The integral of e to the u du is e to the u plus c. And let's see, how did I know that? Well, let me ask you this for the sake of comparison. We know what the antiderivative of e to the x dx is, right? It's e to the x plus c. What's the only difference between this and this? Just the name of the variable, right? So whatever this expression does to x, this expression is going to do to u. This expression yields e to the x plus c, so this expression will yield e to the u plus c. And now we rewrite everything in terms of the original variable. And son of a gun, we started off with e to the tangent of x over cosine squared x. That's what we started off with. And in terms of u, we got e to the u plus c. Now, how do I write this in terms of the original variable x? Back in step 2, we have our rate of exchange between u and x. u is the same as tangent x. So wherever we see a u down here, we're just going to put tangent x up here. Let's just sum everything up. The antiderivative of e to the x is e to the x. And if u is any function of x, the antiderivative of e to the u du is e to the u plus c. So this tells us how we do U-substitution when we're integrating an exponential function.